I'd like to welcome everyone to the CCPO and ICAR seminar series today. Today we are pleased to have Dr. Travis Miles from Rutgers University as our seminar speaker. And Dr. Miles is in the Department of Marine and Coastal Sciences at Rutgers, but he's also part of the Rutgers University Center for Ocean Observing Leadership, or the Are You Cool group at Rutgers. And a group there has had a long history of observing the ocean, and through various methods such as autonomous vehicles, observing networks, and then putting the information from the observing networks in, or incorporating it through assimilation into models that are developed for the Mid-Atlantic Bight or other coastal areas. Today, we're going to hear about some work that's being done in support of offshore wind energy development in the Mid-Atlantic Bight. And there was about a year ago, there was a report from the National Academies of Science, Engineering, and Medicine. An Academies report focused on what needs are for offshore wind energy development, and from the ocean side and atmospheric side in terms of providing data that can go into models. And one of the big unknowns in this is the effect of wind energy development, or the turbines, on the air-sea exchange or the air-sea coupling. And I think that's some of what Dr. Miles will talk about today. So I'll end at this point and just say that we are pleased to have Dr. Miles today, and his seminar will be on offshore wind in the Mid-Atlantic Bight cold pool, which is an important hydrographic feature of the Mid-Atlantic Bight. So please go ahead.
Yeah, thank you. Thank you for having me. And it was, great to be at that National Academies meeting and, hash out a lot of what's going on in the offshore wind world. So thanks for the invitation, Eileen. So let's see. I'm going to get started here. Just as a warning, this is the first time I've kind of assembled all the information you're going to see today in one talk. So I'll do my best to keep time. Tell me if I'm going long or something, and there's a couple areas I can kind of click through. I'm gonna get into the talk in a minute. So I've been at Rutgers for about 15 years. I started in 2009. I've been working on offshore wind since about 2014 consistently, and I haven't given a lot of talks on it as far as the physics and things like that. So I'm really excited to kind of get this together to kind of share a lot of the work we've been doing and knowledge on that. But my main work has been on hurricanes and air-sea interactions, upper ocean processes. And while that talk is not about this talk is not about hurricanes, I did want to highlight kind of what's happened in North Carolina with Helene, and then also Milton. I don't have that on here. I'm a North Carolina native, so impacts from that storm are really, really tragic and difficult for Asheville. So I'll put this back up at the end of the call. But if you have any interest in giving, on the left is United Way of Asheville. So that's more local giving to the community. And on the right is Western Carolina University, specifically helping the student affairs in those impacted regions. So just want to put that out there before I get into my talk on offshore wind. Okay. So yeah, as mentioned in the introduction, I'm with Are You Cool, the Rutgers University Center for Ocean Observing Leadership. People who know us probably know of Scott and Oscar the most. They're our co-founders of the group, but we've expanded quite a lot over the last 30 years of existence. So Grace Saba and Josh Kohut have been core members for a very long time, working on ecosystems, physics, fisheries. Janice McDonald has been a member for a very long time, integrating all our knowledge into broader impacts and outreach activities, and really been fantastic for that. I've been with the group as a PhD student all the way through to starting as tenure track faculty in 2018, focusing on ocean observing and storms. And then we have Alex Lopez, who's heading up our master's program, which is a 1 year master's in operational oceanography. And then the two newest members who are not new to Rutgers at all, but we've kind of had so many projects around offshore wind, we've absorbed them into our group. And that's Daphne Monroe and Motts or Tom Grothis. So I think Daphne's group is on the line right now and has projects with ODU as well. So it's great to have this kind of full built out team working together on some of these challenges. Now, this is kind of the faculty leadership, but we have a large group of about 50 people if you include our staff and students. So 50 researchers and educators with this shared mission. And that's to improve our understanding of our ocean planet for good of its people and advancing ocean observing globally for a safer, more resilient, more prosperous, and equitable world. We're working on that mission statement right there, which you can imagine how this area of offshore wind comes into that mission statement. Some of the areas that we're working, safety life at sea. We have a large HF radar network that we operate through Marcus, through that partnership. Gliders, looking at the coastal ocean, innovating and developing new technology. So this is one of Daphne's projects, looking at developing new dredges that can actually work in and around offshore wind lease areas. Climate change in the Arctic, where I've worked with some of you all here, Mike Dinneman in the past, among others. And then all of this wrapped up into training the next generation. So we try to bring students into everything that we do. You'll see some student work in here today. Okay, for the remainder of this talk, the first part is really going to be giving a brief overview and kind of status update on offshore wind. So some of it's going to be just background knowledge on what's going on with offshore wind. With the note that what's going on with offshore wind changes very, very rapidly. So anytime I make a slide, it's like out of date by the next day. So at some point, I'm just kind of using some general information, and we can have a discussion about any details, or there might be people on here that know more details than me that are localized to different areas. So I'll give a overview of that, and then I'm going to share two like kind of 10-minute research topics. An investigation of impacts of offshore wind on the Mid-Atlantic Bight cold pool. So how turbine foundations may or may not impact the cold pool. And then the opposite of that, how coastal upwelling or how the ocean may impact offshore wind power production. So I kind of wanted to give two different flavors of interaction between offshore wind and our coastal ocean and the cold pool. So for that overview, some general offshore wind drivers. Why are we building offshore wind at all? Generally, in the offshore zone, one main thing is they don't occupy the physical land resources where we live. We know there's a premium on housing and construction and land use. That's not to say there's no impacts offshore. They're just different. The other big thing is in the offshore zone, turbines can be built considerably larger physically, and some of that is regulations, and some of that's just sites and things like that. I'll get into this a little bit more in a minute. Some offshore wind challenges. There's lots of them. These are kind of a top few here that are on my mind. Supply chain issues is probably one of the biggest challenges right now. Is that despite all the projects moving forward, there's a limited supply chain of actual physical turbines. So you might hear about projects getting shut down or delayed or something like that. A lot of times that's coming because the turbines are just not available, and that's making kind of the financing difficult. But aside from that, there's a lot of physical and biological concerns about where you're developing offshore wind farms, the fisheries impacts, the ecosystem impacts, all the way up the food web. Multiple ocean uses, recreation, sediment, things like that need to be considered. Challenges at interconnection points to land. So cables coming through communities are a big challenge, and equity kind of on the land side. And then there's also just kind of some unknowns about wake effects from these newer, larger turbines that are less studied. So the turbines that are getting proposed and developed for the East Coast of the US have never been really installed anywhere else in the world at those kind of larger sizes, and we'll see some of that. So there's some unknowns on the research there. but a little bit more about why we're hearing about this so much in the Mid-Atlantic Bight. Um, Generally, we have some of the highest population density in the country, going through the Mid-Atlantic and the Northeast in general. That means we have an intense power demand. So our customers are very, very close to shore, close to the offshore sites. And basically, the further your customer is from your power generation, the less efficient it is. There's power loss along the lines. Anytime you have to transmit electricity at distance, you lose power and makes it less efficient. Um, we also have a very strong wind resource in the region. It's not the strongest in the country. You can see there's also some strong wind resource off of California and on the West Coast. But we have a very strong wind resource. In this case, this is talking about averages at 200 meter. I don't remember. I think this is 100-meter height, 200-meter resolution. But it was around in these 9 meter per second ranges, actually. Um, and it's co-located with this wide and shallow continental shelf. So, a kind of core thing with offshore wind or any structure is it's expensive to build deep. So, the shallower the water, the cheaper it is to build. And most of the costs of offshore wind are really coming from that construction cost. So, we kind of have these four reasons of why we're seeing this industry spin up into this region here. Um, Now, if we step back a second and just think about how we get our electricity in the U.S., this is a history. This is a 20-year history from 2001 to 2019 for the entire U.S. This came from a good article in the New York Times, and you could pick out really any state and look at the mix of energy. Um, and what you see are different types of energy, and then their percentage of the market at that time. And so you had back in the 2000s, you had coal at like 50%, nuclear at 21, natural gas at 17, and then these others kind of down below. You've seen some really big changes in the markets. We've seen coal basically cut in half, so 51% to 23%. Natural gas really spike up. And a big part of coal's drop is because of natural gas's rise. So we're majority natural gas right now as far as our electricity generation. Nuclear has really stayed stable, and I don't know about local sites and nuclear generation in Virginia, but I know up here we're basically shutting down old nuclear facilities. They're reaching end of life. So those are continuing to actually drop. If we move past 2019, I think a few got shut down here. And we're not building new nuclear. So we need to have something to kind of replace that. And you can see wind start this inflection point, and this is land-based wind at this point. Really, nothing is built in the water. So it starts this inflection point of increasing. It's about 7%. Solar is not on here in any detail, but I think it's going to be on the next slide. Yeah. So this was for the electric grid, PJM. This is our regional transmission organization. You share it in Virginia with us in New Jersey. So this whole region is the PJM region. It's our regional transmission organization. And this is the instantaneous image um, of how much energy or generation fuel mix at 3 p.m. on October 17th. I could show you exactly what it is right now. You can go to this website and you can see hour by hour what the actual generation fuel mix is. So this is a snapshot. Um, and total at this time, there was a generation of about 80,000 megawatts. So I'm putting this on here to give you some context for the future of me talking about some of the projects. That's 80,000 megawatts or about 80 gigawatts total. Renewables are about 10,000 of that, and that's mainly solar and wind here. Solar is this kind of pinkish magenta slice here, and then wind is smaller here. Um, yeah, this changes hour by hour. It's pretty cool to kind of watch it go. But I want this for context. But keep that 80,000 megawatts in perspective as we go through the rest of it. So this is loosely what's being planned. Like I said, these numbers change and as we go, but this is loosely what's being planned currently. There are 24 lease areas and expected about 3,500 turbines. Federally, there's a goal of 30 gigawatts, but if you look at the actual state commitments, so 30 gigawatts is 30,000 megawatts. State commitments are about 40,000 gigawatt or 40,000 megawatts. But those target dates are a little different. So there's some in 2035, some in 2025 and 2040. But generally, we're looking at 30 gigawatts by 2030. So that's about half of the total is the plan by 2030, or the target by the federal government, and that's about three times what we currently have, half of PJM, and three times what we currently have in renewables in PJM. So it's a big increase in renewables. In this region, there's a couple other things going on. As you might know, it's the third largest U.S. port in the Mid-Atlantic region. Um, there's 20% of the population in the Mid-Atlantic region. Just in New Jersey, the sport fishing value is 1.1 billion. So there's a lot going on. There's commercial fisheries. There's the scallop fishery is one of the most lucrative fisheries in the region. I think it's something like 70 million. Daphne could correct me, or someone could put it in the chat from Haskin if I got that wrong. There's a lot going on in this region where offshore wind's being proposed and built. Something I didn't put on here is all these lease sites here are ones that have been leased and are under some stage of development. There are other kind of planning areas for floating, identified potential floating turbines. So that's a whole nother ball game. Um, and that is something that's coming down the line that I don't really talk about today, but to keep in mind. So to think about what I'm talking about with 3,500 turbines, what that actually means. These are kind of the different scales of turbines, and from left to right, you're basically it's land-based to offshore, and then timelines down here as well. So on land-based wind, up to 2020, if you see a turbine and you drive by it, anywhere in the country, it's kind of these 3 megawatt, maybe a little higher turbines. They may seem massive, but they're actually relatively small compared to what's being proposed offshore. So here's the Statue of Liberty here for reference, and this is height in feet. 2016 to 2035, we've basically been going from in the offshore zone proposing 6 megawatts to 17 megawatt. Actually, I've heard up to 20 megawatt turbines. Most of the work I'm going to show today, anything where I'm talking about a turbine, I'm thinking about a 15 megawatt because that's just what we were using when we started. But this is basically a hub height of about 500 feet, and then these rotor diameters of a few hundred feet apiece. To put that in some more perspective, I cut out the Statue of Liberty. And basically, I think of it as an Empire State Building with three Statue of Liberties spinning around on it. That's the scale of a single turbine. So it's pretty impressive to think about. Pushing this growth in size, is basically that the cost per megawatt is better with larger turbines. It's a single turbine construction cost. It's a nonlinear relationship between the construction cost and the power generation. So basically, if you can get bigger turbines, get more power out of them, it's less steel in the water, less construction. I don't know where that inflection point is, where that relationship breaks down, but that's kind of what the industry and market is talking about. So for New Jersey, I'll just focus on New Jersey and Virginia today. So New Jersey, it's 7,500 megawatts, our goal by 2035. Virginia, it's 5,200 by 2034. So basically divide this 7,500 by 17, and that's the number of turbines that those places are planning on getting power from. And that's the nameplate ratings. You can expect to get about 30 to 50% of that nameplate a year kind of in power is what the estimates are in the offshore zone. We can go into that if anyone has any questions. Here's the process. It's quite lengthy. Most of the lease sites in the Mid-Atlantic Bight have already gone through this planning and analysis and leasing phase. I think everything's leased, even though there may be some shakeups of different lease sites. So that's about 2 to 3 year process once they kind of start that. And then there is about a 5-year site assessment and survey timeframe with BOEM, Bureau of Ocean Energy Management. And then there's 2 years of once they submit, a developer submits what's called COP, Construction Operations Plan. And then there's 2 years environmental and technical review. I'd say all of this is best case scenario. I think we're seeing a lot of longer timelines because of kind of market shakeups and things like that. But the point I think here is that every phase of these are opportunities to do research. So doing site assessment and surveys is an opportunity. There's opportunities for universities to participate in some of this type of work or get data from BOEM about it. BOEM environmental and technical reviews. There's stages where companies are I'm happy that they're funding universities to do some of the environmental monitoring, like we do some of that at Rutgers, rather than it only being companies. So there's a lot of opportunities for researchers to work in those spaces. And then there's also other opportunities. I think we have a 10-year fisheries monitoring plan that's supposed to be pre-construction, during construction, and post-construction, and supposed to go on for these long time frames. So it's politics of offshore wind aside, it's a great opportunity to collect data before, during, and after by universities and get that data shared and out there. Yeah, different phases. Each project is kind of at a different time point on this timeline, but it's the general picture. Okay. Um, Speaking of research and getting into more in the science of the cold pool, there are certainly a few areas of uncertainty and research needed. These are a couple of the different reports. Some, you know, three of them I worked on, so I put them on here. But the national academies that Eileen was talking about, this consensus report for Nantucket Shoals region, is one looking at potential hydrodynamic impacts and kind of highlighting what the needs are in research. We've done others on uh, basically looking at can wind farms influence continental shelf oceanography and ecological processes. These were kind of the same report, but one was peer reviewed on the right. And then another report that I've worked on with for the American Clean Power Association. So one was for fisheries, SCEMFIS, and the other was for industry, and they both said the same thing. So there's that. But one thing that we kind of found through all of these basically literature reviews, a lot from Europe and a lot of some of the early stuff happening here, was there was not a lot known about what might happen on the hydrodynamic impacts side. And so I'm going to focus in on that specifically with the cold pool here today. Um, so this is maybe more for the general public here. I think a lot of our physical oceanographers, we know about the cold pool. We know it's been studied for a long time. But when I talk to the public about this, they don't realize that this feature has been studied since 1933. So studies of the waters on the continental shelf, this was by Henry Bigelow, and it was done with lightship data and all sorts of data throughout the Mid-Atlantic continental shelf. Kind of the first identification of the Mid-Atlantic cold pool. Um, so almost 100 years ago. There was certainly research since then. The 1979 study by Houghton, and then some other studies by Manning and Mountain, basically identifying the bottom cold pool as this. Their kind of formal definition at the time was waters colder than 10 degrees C and salinity less than 34 PSU. So it's kind of water mass fingerprint way of looking at it. And basically, this is a seasonal feature. So this is March, May, June, July, August, September, October. Seasonal water mass feature that sets up on the continental shelf. Very cold bottom water that's important for our ecosystems, brings nutrients into the region, allows kind of habitat expansion from the north, cold water species to basically move further south than they would otherwise, and is kind of this thermal niche for certain shellfish. Can really set the life cycle of shellfish, and is basically our essential ocean feature of the Mid-Atlantic region. Looking at it in a little more detail, this is from Steve Lentz paper in 2017, and it shows that cold pool setup. So May, you can kind of see the outline of this cold water mass. June, a little bit sharper. July, it looks like it starts to go away a little bit, but it's interesting because that's actually the peak stratification time, even though the cold bottom temperatures are starting to erode a little bit. And then August, September, October, where it starts to really go away. Generally, what's happening is it's the temperature is set by localized cooling in winter and then transport from the north through spring. So you get that cold water over winter and then southward transport of Labrador seawater into the region. In summer, you get rapid heating, spring and summer, rapid heating basically caps off that cold pool and it maintains its presence throughout summer. There's kind of gradual warming about 1°C per month. It's generally from vertical mixing by tides and winds. And then in the fall, it breaks down very rapidly from storms. Sometimes it could be a couple of storms that come through and break it down, or one really big one. Here's another view of that from cross sections off the New Jersey coast from glider data. So you can see that capping off right here in June. You can see that warm layer forming, cold pool water at the bottom. This is distance from the coast. Really peak stratification in temperature in August, and then it's gone in October. Um, Now, this feature doesn't just sit there. It doesn't just sit there in one place. It actually is quite variable. So this is a 3D surface of the cold pool from John Wilkins' ROMS model, Doppio, in July of the 12°C isotherm. And you can kind of see it just moving around, sloshing around back and forth. It's actually very reactive to wind forcing, downwelling, upwelling, things like that. Which is interesting in how that it might be exposed to an offshore wind area, or it might be upwelled at the coast, which I'll talk about a little later on. So that cold water might be upwelled at the coast, or it might be pushed away off the coast. My thesis work as a PhD student was actually about how the cold pool was advected offshore like 50 kilometers or more um, during Hurricane Sandy, right before it fully broke down. So it's quite a dynamic feature, despite this kind of like static picture we have in our head about it. Okay. So this I won't go into any detail on this, but generally it's an important feature for those ecosystems, which is why a lot of our funding on the from offshore wind and other projects has been really to look at those ecosystem impacts and monitor the cold pool pre-construction for ecosystems. So this is a project from NJ. This is the New Jersey Research and Monitoring Initiative. I was saying before the call started to Eileen that basically New Jersey puts in, basically developers have to put in about $10,000 per megawatt of power they want to develop into a research fund called the New Jersey RMI that's administered by our state Department of Environmental Protection and our Board of Public Utilities. All those proposals are due tomorrow for this round of funding, so everyone's really stressed out right now. But some of the past funding has gone into this research and monitoring initiative with gliders. So this is the NJRMI Eco Glider project. And these are just some of the tracks. I think the pink and the black ones are DEP funded tracks through NJRMI. All the background tracks are just other missions that we've done throughout the region. So since 2011, there's been about 81 missions, 1,700 glider days, and 427,000 profiles through this region of things like temperature, salinity, density, connectivity. So we have some pH measurements on some of Grace's gliders, dissolved oxygen, chlorophyll, things like that. And then really select gliders with active acoustics for fish, fish and zooplankton, as well as a lot of marine mammal monitoring for things like the North Atlantic right whale, which has been a really big issue off the Nantucket Shoals region. So a lot of work going on in the ecosystem space. Not as much going on in the physics space. So I'm going to move on from the ecosystems, talk about it all day, but physics is where I want to talk. What's being structured, what's structuring the habitat that these organisms are living in. So from some of the review literature that we did on this, there were kind of three core points that we found that might influence how offshore wind might influence the cold pool or stratification. I won't, there's a lot of text here because it's our actual findings in one of our reports. Um, but the highlights are that number one is that wind extraction basically reduces wind speeds locally. That happens, at the turbine hub height swept area level. But the question we had is, does that wind extraction actually project all the way down to the sea surface and cause disturbance at the sea surface that might affect things like upper ocean mixing, stability, things like that? It wasn't clear from any of the kind of wake models or observations that was possible or not. There's a paper by Golbazi, Christina Archer, and Miriam Golbazi from 2022. They studied this with a model. And basically, from their model, they showed that they looked at wind wake effects in summer months off the New Jersey, whole mid Atlantic actually. And they saw wind speed reductions at the sea surface about half a meter per second on average, really limited to within the lease areas. So they filled these lease areas full of turbines, and then looked at where those impacts were. So they did see some reductions in wind speed. Um, Generally, it was contained to within the lease area, so not this long, extended kind of massive wind wake effects. This was using a pretty simple parameterized model. Definitely needs a lot of work and a lot more detail to understand how those wind wakes might get projected um, uh, vertically. But generally, their findings was the bigger turbines actually have a less impact at the sea surface, and that would result in a potentially minor stabilizing effect of the water column. You're basically reducing the wind stress, um, making it to the sea surface by wind speed reduction. Now, there's a lot of other things in their paper about kind of boundary layers, marine boundary layers, changes in heat, all sorts of other things that are worth looking into and digging into if you're interested in that. The second thing we found in the literature, mostly from Europe, is some early studies that basically were looking at, okay, if you have that reduced wind speed from a wind farm, what might that do to vertical advection of isotherms? And there's some studies showing that you might get a dipole of downwelling on one side and upwelling on the other. Um, I I think those studies need a bit of a revisit. They were looking at really kind of farm scale processes, treating an entire wind farm as like a drag. Um, and I think based on kind of the Golbazi findings of the mean wind speed reduction at the sea surface being low, this may not be something that manifests. You imagine you need a persistent wind in a particular direction for more than an inertial period to get, downwelling and upwelling to really, really set up in a real way. Um, and so it's still an open question. It's not one I'm chasing down. But I think if the right tools exist to study it, someone should take it on. Um, but that's not what I'm talking about today. The third one is what I'm going to talk about today, and that is more about the structure in the water. So things like monopiles, there's an idea that things like monopiles may increase ocean turbulence and mixing. Um, and I have a nice little schematic here from Jeff Carpenter et al. 2016, um, who's participated in a lot of these kind of panels and reports. And they looked at this in the German Bight. And basically, what they were looking at is they have a stratified water column. In the German Bight, they have pretty fast tides that are going past turbine foundations on a daily basis, just back and forth, back and forth. And they wanted to know, does that regular tidal velocity have an impact on mixing as it passes a foundation structure? This is a very simple analytical approach that they did, which I'm reusing here, but they're also working on some large eddy simulation of this to try to look at it in more detail. Basically, what they found is that there could be a significant impact from turbine foundations on stratification in the German Bight. The caveat to that for the mid-Atlantic is that tides in Europe are very fast. In their locations, they were looking at half a meter to a meter per second velocities past those turbines foundations. And from some of the equations I'll show later on, The frictional force in mixing is basically proportional to the flow speed squared, or actually cubed. You'll see in the equations later on. So it's a nonlinear relationship with fast current speeds. Mid-Atlantic, we have tidal speeds that are much lower, order 10 centimeters per second or lower. So we didn't think just kind of off the bat that tides would be a problem with mixing, but we did are curious about strong currents during storm events, like Hurricane Sandy, things like that I mentioned earlier, or nor'easters. So that's where our research on this topic is going to go in a minute. Um, I'm not going to go detail here, but the first thing we did was we wanted to know about how much does the cold pool actually overlap with wind lease areas. We went to the Doppio ROMS model, a 16-year reanalysis that John Wilkin's been working on, Wilkin and Levin 2022. And we took a look at this model just to see, based on some simple definitions of the cold pool, how much and how often and when do you get overlap of that cold pool. So this was a paper published by my graduate student, Becca Horowitz. She was actually working on this as a NSFRU intern and published it right as she started graduate school. Um, and basically what she found, do I have the highlights on here? I might have deleted them. Awesome. Um, she took a definition of the cold pool that was basically those bottom temperature definitions, but she also took a stratification definition of zero point 0.2 degrees C per meter in the vertical to identify the cold pool as present. And this blue shading is when the cold pool is present in the kind of monthly averages of that 16-year reanalysis. And you can see our peak overlap with lease areas. This is where basically what this is saying is 81% of wind lease areas had the cold pool present, but that only represented about 13% of the total spatial area of the cold pool. So a lot of overlap of the cold pool with wind lease areas, but only a small portion of cold pool actually um, in the whole time period. So you can see 62% in June, 41% in July, and it really starts to drop off. New Jersey actually kind of loses some of its overlap in June. But just keeping in mind, like I said before, this is a dynamic feature. So just because it's not overlapping on average doesn't mean it's never overlapping at that site. So we still want to dig into this a little more. So this is where we go back to that Carpenter model. And we have our NJRMI project. This is myself, Fernando Pareja Roman, who's assistant research professor here at Rutgers, and then staff member and student Julia Engdahl, who worked on this. And we basically wanted to take the approach of Carpenter et al. And apply it to the Mid-Atlantic Bight. We did this this way because some of the offshore wind turbines, basically, there's not an easy way to use our standard regional models to evaluate mixing from turbines. There's been a few studies working with like FBCOM and things like that, but it's a really challenging thing, and it's not what those models are designed for. ROMS is not designed to understand a 10-meter, 15-meter diameter monopiles impact on the water column. So we really wanted to start off with something analytical or like an LES model. But we figured we'd take the analytical approach first just because it's computationally efficient. We can do it quick. We can run it on our laptop very quickly. And then we can later on focus on the more detailed studies for cases that we find might be important. Um, so how does this analytical model work? This is a couple slides of equations. But basically, your tidal flow past the cylinder is the top equation. I showed that before. You have a drag coefficient, CD. You have A, which is the turbine monopile area. You can see it right here. And then you have the mean flow, and then the variable, basically, yeah, currents pass. It ends up getting cubed into power removed. So you get the flow past the turbine right here. When you change that into power removed, you basically multiply both sides by U and you get U cubed, and then FU power removed here. And this is kind of a rough basically you go to per unit farm area, and we call this P stirring in watts per meter squared. And then there's two different drag coefficients that are used to look at kind of high mixing scenarios and low mixing scenarios, since we have some uncertainty in kind of our turbulence formulations here. And so on one side we have P stirring, which is basically the mixing part, and then we have the resistance to that mixing part in the analytical model, which is based on the potential energy anomaly. And which is essentially the energy needed to fully mix the water column. So you have your average water column density, and then you minus the instantaneous density. This was like Simpson 1981, and it basically gives you an estimate of how much energy it takes to fully mix that water column, mixing everything to completion here. When we combine all this up, in a lot of steps I'm probably going to leave on the cutting room floor, you get this T mix here, which is generally in units of days. And this is basically how long would it take to fully overturn the water column due to the addition of turbines only. So if you have a flow speed and turbines, you don't worry about storms, you don't worry about tides, you don't worry about anything else. How long would it take for the addition of those turbines to overturn the water column? If people have questions on that later on, I can try to explain it in like 4 different ways, because it's not a normal way of us doing things. Um, in the German North Sea, they found for the low turbulence, for the low drag, about 688 days is how long it would have taken for their regular currents. And then for the high turbulence, 151 days for tidal currents, about half a meter per second. So not a high likelihood of overturning the whole water column, but kind of giving you a rough estimate of whether there's going to be some impact or not. Maybe you want to focus in on this low turbulence. Maybe you want to focus in on higher currents if there's storms or things like that. Or maybe we need to do detailed LES models because, hey, this is a simple analytical approach, and it could be off by 50% or something like that. Could be a big challenge. So we wanted to take the same approach, but replace it with our own numbers for Mid-Atlantic Bight stratification. So basically, we wanted to find our own potential energy anomaly numbers, our resistance to mixing numbers. And we did that with the about 15 years of glider data that's been collected in the Mid-Atlantic region. Julia Engdahl sliced out all the glider data in July and August and September, October that went through this New Jersey lease area. So all these different colors are different glider deployments in that time period. Same here. And we got about 13 and 15,000 profiles in each of those kind of 2-month windows. We use that to develop our composite profile that we calculate the potential energy anomaly from. And we do it this way. Basically, we get a surface layer characteristics, bottom characteristics, and then the thickness of the picnic line. We do it this way instead of just averaging all these profiles together, because we want to minimize the impact of like internal waves and tidal variability and things like that we didn't want to smooth out the thermocline or the picnic line when we did this composite profile. So yeah, we kind of focused on the surface, bottom, and then we built these composite profiles. It's not peer reviewed yet. I don't know if there's better ways to do this. This is the way we did it over the last couple of weeks and started to get some figures. So here is July and August, and September, October. This is our potential energy anomaly. It's about 127, and then 47.4, so about a third during the breakdown period, or September, October, and then about during July and August, the peak period. So it's about 1021 and 1024, and then a smooth picnic line, and then same here. We're at about 1022 to 1023, so about 1 PSU through that gradient. We use these in our analytical model, and I'll unpack this one. Our analytical model, rather than trying to find data for currents, what we did first was we just said, let's run our model for velocities all the way from 0.1 to 0.8 with those two different stratifications. And let's just see what we get as far as mixing days. So this column, it's a log plot on the left. This is number of days to fully overturn that cold pool water column. Um, for a zero point 0.1 meter per second current in a mid-Atlantic bight kind of peak stratification, it would take more than 10,000 days of flow past those foundations to overturn the water column. So not likely at those slower speeds. You can see I'm kind of brushing over this. There's actually an unsteady and a steady model, and then two different drag coefficients, but it all is kind of packaged up into the same order of magnitude. And you can see even for velocities, or even for the um, 0.8 meter per second current, it would take 10, roughly 10 days to overturn the water column. And this is depth average current assumption. So it's getting into a real value of, yeah, you could, if you have some crazy storm or something, but really 10 days of continuous flow is also unlikely. September, October, it's about the same. And our plotting is terrible here, I think. But I add in this line, we went back to Doppio and we said, okay, how often do these depth average currents actually occur? In these 2 month periods, we basically got the 2 month counts averaged across 16 years and plotted them here. These are not necessarily like consecutive days of current speeds just flowing. This is just how many times did a velocity of above or of like bend in this threshold actually occur during those 16 years. Um, Really almost nothing in this zero point 0.6 to zero point 0.8 range in June, July for a depth average current. Half a meter per second, you get a little bit of that, but nowhere near this kind of mixing time scale here that we're seeing. August, September, you get a little bit more at that high end, and that's largely due to things like hurricanes and storms ramping up. I might be Can people see my slideshow?
Yeah.
Okay, someone said they could not, so maybe
Thank you. Yeah, I'm not seeing it, but I'll check other avenues.
Okay. We share the slides for sure after, and I know there'll be a YouTube link. So sorry. So anyway, the key findings here. I won't go back over too much of this, but generally, we don't expect cold pool overturn due to the addition of turbines, kind of at the scale that we're seeing right now. Um, that doesn't mean there will be no mixing. Again, this is like full water column overturn. So there might be still opportunities for mixing. There might be enhanced nutrient injection, and then we don't, with the analytical model, we can't look at horizontal and vertical flow disturbances. So there might be flow disturbance from around turbines and things like that. We don't look at that here, and definitely future studies on that. There still should be a focus on higher current speed timeframes and shoulder seasons when stratification is weaker. So our study, I think, sets a good target for future more detailed kind of LES style approaches. I know I'm probably running along low on time. I'm still going to try to get through this real quick unless someone wants to cut me off. Yeah, Eileen, how much time do I have? Am I okay?
Yeah, you're
A few
fine.
more?
Yeah, no, please go ahead.
Okay, I'll try to get through this quickly. So this is the reverse. So instead of ocean mixing, this is looking at the impact of um, coastal upwelling actually on turbine power production. And we kind of started to catch wind of this idea with Greg Soroka back in 2018 paper, one of our former PhD students. And basically we noticed that first upwelling basically occurs. This blue line is frequency of upwelling days, occurs at the same time in summer in the Mid-Atlantic Bight as our highest peak energy demand. So the black line is basically energy demand to that PJM area. And it's hot summer day. We're using air conditioning and things like that. While people go to the shore in New Jersey, and they really freeze because those are the same days where we get coastal upwelling. Here's an example of coastal upwelling in the Mid-Atlantic, cutting right into some of these nearshore lease areas. And we were thinking about, okay, you have a really cold water. How might that affect the marine boundary layer across a atmospheric or across a windswept area of a turbine? Um, we looked into how frequent upwelling occurs. And this is kind of qualitative visual inspection of satellite imagery. And it's about 50% of the time, actually, in summer, June, July, and August, you can get coastal upwelling along the Jersey Shore and a lot of the mid-Atlantic. There's a lot of variability in that number. This is only 3 years, but still, roughly 50% of the time. That's quite a lot, especially when you're thinking about power production and lots of money going into power production and developing offshore wind. So we have been running an atmospheric model, this particular one since 2018, but we've actually been running a version of this since 2011. And this is a weather research and forecasting model focused on the New Jersey coastline. And it's specifically designed with its layers and output in mind, looking at windswept areas of turbines. So lots of layers in this rotor diameter region for like a 15 megawatt turbine. Won't go into this other than to say one of the big things that we do is we have a special sea surface temperature product that goes into this weather model. It's not a coupled model that is designed to maintain that coastal upwelling, which actually gets frequently removed by the standard quality flags. So we were using the GOES geostationary satellite here. And we set up a simple experiment where we took a day in August 2022 that had actually 2 days that had a strong coastal upwelling, and then we removed it. Basically, anything cooler than 25 degrees C, we set to 25 degrees C. So here you have waters that are much cooler, 20 degrees C. And we ran a twin modeling experiment to look at the boundary layer and look at winds and things like that. So here is skin temperature minus air temperature plots. On the left, this is basically data along this transect, so 0 to 60 kilometers, 0 to 60 kilometers offshore. And then time, 12 a.m. to 6 p.m. on a particular this day. And then this area is that wind lease area, and this is kind of the upwelling inshore. And basically, we did skin temperature minus air temperature to look at stability. And in our upwelling case, we see a stable, basically a stable marine boundary layer, or at least right near the surface region on this inshore zone. And when we remove that upwelling, it's basically unstable, which is important for basically increased stability could lead to larger wind wakes and reduced power production, but it also might change the marine boundary layer height. So that's what we looked at next, the marine boundary layer height. During the upwelling case, that kind of general definition of the marine boundary layer height was right in this rotor diameter layer, so 200 meters here, and that kind of comes into this lease area as we define it. When that upwelling is removed, the marine boundary layer height is like 800 meters. So a big change in the marine boundary layer height due to just that kind of band of inshore temperature in this region. And then there's similar offshore. So potentially we're with a lower marine boundary layer height, we're bringing down faster winds from aloft into this windswept area. But also that could increase vertical shear, which could decrease power production. So when we look directly at the wind speeds, so this is upwelling and then upwelling removed, you can see these actually stronger wind speeds in this. This is all hub height, yeah, stronger hub height wind speeds during this particular time period. Mostly inshore, not as much in the lease area, but mostly co-located with where that upwelling was occurring relative to the upwelling removed. And then when we look at shear, this is basically two heights of winds subtracted. You have blue. The blue is, I forget which one's top and bottom, but basically you have a top layer and a bottom layer, and you can see that veering. Basically, we're getting wind shear across the rotor diameter, which could increase, first decrease power, but also enhance maintenance costs. So if you have shear across this turbine, you could have wear and tear on the blades, and long-term maintenance costs are increased. And I'll wrap up there. Yeah. So big picture summary is there's a lot of monitoring underway, growing body of physical oceanographic work. We can adapt findings from European studies, but we can't really adapt the findings, but we can adapt the methods. My general takeaway is there's low expectation for turbines to overturn the cold pool, but potential for enhanced mixing. Um, and then, yeah, I'll leave it there. And thank you, and take any questions.
Okay, thank you. It's very interesting. So, um, if there are questions, we have time here for a few questions. If anyone has one, either turn your camera on or raise your hand or whatever.
I have a question.
Yeah, please go ahead.
Okay.
Yep, Miriam.
Travis, hi.
Hi.
Great talk. Thanks. I'm actually curious about this sea surface temperature data. I'm wondering if it's publicly available now, because at the time I was working on my paper with I think that Dr. Matt Oliver was also part of the group. I'm not sure if it is the same data, but
Yeah, it's the same. It's the same data and a version of it. I think he hosts it live. He hosts the.
Mhm.
I don't know if he hosts the hourly data or if just the daily composites. But if it's not available, it's more out of our effort rather than our available effort rather than us not wanting to make it available. So if you want it, by all means. And also, if anyone has any questions about wind wakes, ask Miriam and not me. So,
Oh, thanks. And one more question is, while working with WRF, did you encounter any kind of numerical noise? I'm just curious.
yeah, certainly our color bars probably are doing us some favors on this, but
Mhm.
certainly we do see numerical noise. So actually, more in the wind wake analysis with Fitch, we see numerical noise kind of far away from the turbines. So we're for the DEP, we're actually looking into our model for the same analysis that you did, and we see some noise in far field, but we kind of see the same patterns that you found like in and around the lease areas. So yeah, it is a challenge, and I don't think I wouldn't use these to any of these, I think, to say anything too specific about wake effects, but kind of just get the general ideas that we've been getting. Yeah.
Yeah, I got it. Well, thanks very much.
Yeah, thanks for your work on this too.
Thanks.
Any other questions? So, Travis, I have one question while we're waiting for other people to think here is, did you look at, just out of curiosity, did you look at how many turbines would have to be on the shelf to have an effect on something like the cold pool?
Yeah, the model is very it is not right it's not a 3D or even a 2D model. It's very much like a localized, you give a turbine spacing, but it's still kind of assuming some kind of like localized infinite impact, right? So we have not done that. I think Jeff has done that a little bit and made some estimates. Um, so I think it's more of thinking in and around the lease area. This could be an expected like change in mixing, but it doesn't translate very well to the 3D world. So um, I think that would be better for like a couple of LES studies to maybe start to estimate what those scales might be of mixing, because the analytical model just really can't give you that information.
Okay, thank you.
Yeah.
Maybe time for one other question.
Yeah, Eileen, a real quick question. Yeah, Travis, I think you looked at monopiles, which are pretty big things. The pictures you showed the four-legged
Yeah.
supports. Do you have any estimation of which one would be less intrusive or less mixing? I don't know, just sort of general
Yeah.
question.
Yeah, I think it's a great question. And I don't have a great answer for you. I mean, the monopiles I think are about 15-meter diameter is the expected diameter.
Yeah,
You can
they're really big thingies. Yeah.
Yeah, you can imagine a few scenarios where like right with there's like foot there's like tripod kind, and then there's and where you're I would imagine if you're the scales are hard, right? If you're increasing the spatial area, you would expect it to go up, but then if you
Hmm.
have a bunch of small pipes, smaller pipes, I don't think it scales linearly, but I think it's a good engineer question. I think Jeff has done that. The other thing that is challenging is that there's also an armor layer that's going in that's not included in any of this. There's a 15
Right.
meter foundation, but then there's also a horizontal kind of rock layer that's could be like 30 to 60 meters. I don't know exactly, but it can be quite large.
Yeah, they
And
tend to be pretty large. You're exactly right.
yeah, and that can change the drag coefficients on the bed. You know,
Yeah.
that can change a lot of stuff. So I think that's another area that people should really be working on, in addition to the monopile versus tripod style and others. Yeah.
My guess
So
is the engineers are going to say it's cheaper to do this foundation versus that, so go away and don't bother us.
I
Is probably the
I
answer.
yeah, I will say that basically most of the ones I've heard of in the Mid-Atlantic are proposed to be monopiles. And that,
Monopiles, yeah.
yeah, and that's been the main focus. I don't know the cost difference between the other ones or why, but I think that's kind of why we've stuck to focusing on this is it's just the one that's been proposed in most of the projects.
Yeah, the one down here off Virginia, they're going to be the big monopiles, and I
Yeah.
think they're already here in the harbor. So
Yep.
anyway,
Yep.
that's the last question. I'll let somebody else jump in if they wish.
Yep. But I did mention before the call started, we did get some wire walker data in about 40 meters of water near a Vineyard Wind turbine. So we have some data to look at, about 3 weeks of data from that, that we might be looking at in the future. So,
Cool.
yeah.
Okay, I think we're at time here. Yes, Jim, did you have a question?
Well,
Yeah.
it's a short question. Is there any work being done on the downwind vortices generated by these very large wind turbines? More of an atmospherics question.
From the atmospheric side, I'm not sure from these sizes. I've seen some work on smaller turbines with basically different types of radar that have been pretty cool. But on the larger turbines, I'm not sure. I don't even know where a test turbine in the real offshore zone would be installed at the kind of 17 megawatt scale. So I don't know.
Okay.
Yeah, yeah. I think we are doing some LES modeling of the in collaboration with Jeff Carpenter of the ocean environment and looking at more details of these larger turbines. So,
Thank you.
yeah.